Video will discuss the statistical underpinnings of modern portfolio theory. So, modern portfolio theory or portfolio theory is the academic area that describes and provides a background to support buy and hold investment strategies. Okay? So that's kind of what we're doing. We're going to start off by making a very interesting observation. Here we have a two-space. On the vertical axis, we have mean historical returns. Okay. On the horizontal axis, we have standard deviation of historical returns. And I'm going to put stock X right there. This is its mean historical return. This is its standard deviation. I'm going to put another dot there, call it Y, and this is Y's mean historical return. This is Y's mean standard deviation of return. Y is the higher return, higher risk security. And what's very interesting is that, generally speaking, we can do something really neat when we start creating portfolios from X and Y that is almost or kind of like counterintuitive. If this holds, if the correlation coefficient between the returns of X and Y is less than the standard deviation of X's returns divided by the standard deviation of Y's returns, if this is true, then it's possible for us to begin adding some Y to a portfolio of only X, which is what this point here would be. That's only X, and we start adding some Y to our portfolio, and we can get a portfolio like that. Now, what's interesting about that portfolio? Well, I'll tell you what's interesting. It has a higher return and a lower risk than our original point X. So think about what we've done. If this is true, okay, and it usually is, by the way, if this is true, then we can add risky Y to low risk X and get a portfolio, a resulting portfolio that has a higher return than X and less risk than X by adding a riskier Y. That's quite interesting. So, and it continues in the general case like this, and then at some point the curve bends up, and we connect these with a line, okay? And that line there has a name. It's called the feasible set. It's all the portfolios that can be created from stock X and stock Y. The only thing you need to know to distinguish, say, this portfolio from, say, that portfolio, called that A and that B, the only thing that you need to know to distinguish them is the weight in X. Because if you know the weight in X, you also know the weight in Y, because this is the two-stock case, right? The two-stock case. It's a simple case, but there's a lot to be learned. This is a valuable case. And you'll see that if you know WX, you therefore know WY, because WY is obviously 1 minus WX. So all we need to know is one of the weights. And that's what distinguishes this point from this point, from this point, from this point, from that point, from that point, is the weights. That's all that's all that matters. Now, if you think about it, the expected return of a portfolio is a simple weighted average of the returns of the stocks that constitute the portfolio. So here we have this summation. Summation for I equals 1 to n, weights of I multiplied by the expected return of stock I. And if we expand the summation here, we have, in our case, the weight in X times the expected return on X plus the weight in Y times the expected return on Y. And that's the simple summation expanded. So it's a simple weighted average. So the expected return on a portfolio is a simple weighted average. One very, very important thing to understand is that the standard deviation of the portfolio's return does not equal, does not equal, I'll circle that in a different color, and does not equal a simple weighted average of the standard deviations of returns for individual securities. Does not equal, no, exclamation point. Make sure you actually understand that. It does not equal. As a matter of fact, it's so important it's going to get its own border. And here. Does not equal. Very important, does not equal. Now, what does it equal? Well, we're going to learn what it equals as we go through this, but I might as well tell you right now what it is. And what it does equal, what the standard deviation of the portfolio's return does equal, is the square root of summing over I, summing over J, the weight in I, times the weight in J, times the covariance of the returns of I and J. That's what it does equal. And now what I'm going to do as we go through this is provide lots of information that will have you understand this formula very well. But this is what it does equal. In the square brackets, we have the variance of the portfolio's return, and we take the square root to get the standard deviation. So now another two space. I just put R bar for expected return. Same thing, standard deviation of return. And there's X, and there's Y. And assuming that our condition holds, the correlation coefficient between the returns of X and Y is less than the ratio of sigma X over sigma Y, then we get a curve that, quote, bends back. And this is the feasible set. Now, we're going to make some observations. Let's consider this portfolio right here. Change the color to red. Consider that portfolio right there. Now I'm going to indicate another point directly above that, on that point right there, directly above it, and I'll connect them with a line. Take it down to the axis. And the thing we'll see here is that these two portfolios have identical risk. I'll call it sigma 1. The risk for both of those is the same, but of course, this portfolio has a higher return than this portfolio, and that means that this portfolio is inferior. This portfolio is inferior to this portfolio. Now that same thing would occur for every portfolio down here up until we get to the minimum standard deviation portfolio right there at the green dot. Because they'd always have a portfolio on the line above it with the same risk but higher return. Therefore, we'll note that if I start at this green dot and I go up like this, assume that this line is coincident with the blue line. So assume the green line lies atop. This green line has a name, and it is called the efficient set. It's the efficient set. Every portfolio in that efficient set is as good as it can get. This efficient set maximizes return given risk. That's why that portfolio is on it and that one is not. So the efficient set is a subset of the feasible set. In this, the two stock case, okay, which is a very important case. Okay, excuse me. All right, well, very interesting. What about a three stock case? All right, so we have the same two space, return on various stocks, mean historical returns, and standard deviation of returns. And let's start with X and Y. And let's add Z here too. Oh, interesting. Okay. Well, if our idea that the correlation coefficient between the returns of each of these securities, say X and Z, is less than the ratio of standard deviation of X to standard deviation of Z, and if we also assume that that same thing holds for X and Y and Z and Y, then we would have something like this. We'd have something like this. We'd have something like this, perhaps. And suddenly we begin to see that our feasible set in this three stock case is not a line, but is rather an area. Okay, color it in here. All right, well, that's interesting. So our feasible set now is an area in the three stock case and the 4, 5, whatever, the n stock case for n integer and greater than 2. So this is our feasible set. Now, what is our efficient set? Well, now our efficient set in this case will involve two things. We want to maximize return given risk. That's what we're accustomed to. We did that in the two stock case. But now we also want to minimize risk given, should be a straight line, return. Okay, we want to minimize risk given return and maximize return given risk, which means when all is said and done, the efficient set for this case starts with the minimum risk portfolio right there, and imagining this blue line I'm drawing is coincident with the dark green line up to Y. That blue line is the efficient set for this three stock case. And the efficient set for the two stock case and the multi-stock case, meaning three and more stock cases, is identical. The efficient set is a line, is a curve. The feasible set here in the 3+ stock case is an area, whereas for a two stock case, the feasible set is a line also. Okay? So here's the efficient set. It's the best combinations of risk and return that exist anywhere. Okay? In the real world. Okay? Every point along here is something that's attainable. And you might say, well, where is the investor going to choose to put his or her funds? Well, let's say this is the efficient set. It's simply going to depend upon the indifference curves of the risk-averse investor. You know, risk-averse investors have indifference curves that look like this. And there's bound to be, like, this is the indifference map, right? And put 3 of them. And this is level 1 of satisfaction, level 2, and level 3. And we know that because we have mean historical return here and standard deviation of returns here, investors are happier as they go northwest, as they go this way, because Return is a good thing. They want more of that. Risk is a bad thing. They want less of that. So these are the indifference curves for a risk-averse investor. Okay? So here, this is the best he can do. He can get to satisfaction level 2 because this is an indifference curve, labeled 2. That means the investor is just as happy here, as he is there, as he is there, and there. And there also, so if he can achieve that, because that's a point that exists on the blue efficient set, it actually exists, it's a possible investment, that he can get that and just get to satisfaction level 2. He can't get to satisfaction level 3, okay? Because there's nothing available in the real world consistent with buy and hold investing that allows the investor to get to indifference curve 3. He can get to lots of points on indifference curve 1. Some he can't get to, but remember, as long as you get to a couple, you know, this, and this, or any one of them gets you just as happy as you are anywhere else on indifference curve 1. Okay, so, and then, by the way, different investors have different types of indifference curves. For example, let me use this. There might be another indifference curves there might be another investor whose indifference curves are a little steeper, and that investor might have a point of tangency right there. Still risk averse, but you know, steeper curves, and that'll put him down here. Obviously, this investor is more risk averse than this investor, but they're both risk averse. And that's enough for this first video on portfolio theory. Thanks for watching.